Okay, good afternoon, welcome back. So, this is our lecture 31 and I will give this the name so we will call this Gallager decoding algorithm A. So in the last lecture what we did was we basically introduced a terminology relating to LDPC codes. So, we talked about edges, paths and neighborhoods. And then we also talked about channel models. And I introduced the channel symmetry condition. And towards the end we were going to talk about the channel output and input alphabet. So, let me copy down a couple of the figures from the end of the last lecture. So, I think these 2 pages it would be nice to have. Okay. So, we were talking about the alphabet from which the messages that are actually passed are drawn from, and I pointed out that these messages are actually subsets of the real numbers. And also I pointed out that there is a common message alphabet that is actually used to communicate messages back and forth between a check node and a variable node. This green arrow here represents the output of the channel. So, that potentially could be a different alphabet. So, we are going to denote that by script O. Now, message passing can actually be viewed as a mapping from the incoming messages to an outgoing message, right. So, in that sense we will actually introduce the following notation. We will actually say that psi sub v of 0 is a map from O to M, and you can think of this as the initial message map. Okay. And then so this is from the variable node to the check node, and what we are basically saying is, look, there is an input that comes from the channel, and whatever the node does, it transmits its output based only on the input of the channel, because that is all it has initially. And this 0 here denotes the number of the iteration. So, we are talking about the 0th iteration here. Now, on the other hand, at a check node, so that is the C here, and during the Lth iteration, the incoming messages, since there are d sub c minus 1 inputs, it is going to map that to M, and in subsequent iterations at a variable node, the map is from the output of the channel alphabet and taking into account the incoming messages, which are dv minus 1 in number, you map this to the message alphabet. So, these are the three maps that are carried out, and so L is the number of the iteration. All right. Regarding these messages, we will make certain assumptions. So, assumptions concerning message passing at a variable or check node. So, we will write these down in terms of the same notation that we have introduced here earlier. So, we will say that psi v of 0 of b m is equal to psi v 0 of m times b, where b belongs to plus and minus 1 and m belongs to the message alphabet. We will also assume that psi v l of b m 0, b m 1, b m d v minus 1 is equal to b times psi v l of m 0, m 1, m d v minus 1. And I will come back and explain these in a second. At a check node, we will assume that the property that satisfies that again here b is plus or minus 1. At a check node, we will assume that b 1 m 1, b 2 m 2, b d c minus 1, m d c minus 1 is equal to the product j is equal to 1 to d c minus 1 of the b sub j times psi sub c of l of m 1, m 2, m d c minus 1. And again this b sub j are either plus or minus 1, and of course the m j are drawn from the message alphabet. So, in words what we are saying is that look, at a variable node, initially we are going to require that whatever mapping is conducted at the variable node must have the property that if the sign of the incoming signal is changed, then that the outgoing signal must also change sign. So, if you multiply m by -1, then the new message is whatever the message was before when m was the input times b. In general, so this is for the initial iteration. So, the initial iteration is when there is an incoming message that is only coming from the channel. There are no other incoming messages. Subsequently, you will have messages incoming from all of these nodes. So, what it is saying is that if each of these is say multiplied by -1, then the output message will also be multiplied by -1. So, that is what this is saying, that if each of the incoming messages, including the message that comes from the output of the channel, if they are all multiplied say by -1, then the message that the variable node is going to send out will also change its sign. At a check node, it is a little bit more complicated. So, we say that at a check node, the requirement is that let us say that we individually flip the incoming messages, and there are d sub c minus 1. So, going back here, you see that at a check node here, you have all these incoming messages. Since the check node has degree dc in a dv/dc regular code, and we are going to assume that we are working with this class of codes, there are d sub c minus 1 incoming edges and 1 outgoing edge. If each of these is multiplied individually by a separate sign factor, so b1 up to b sub d c minus 1, then what happens is that these signs factor outside and you get the product sign which actually goes back, which is multiplies the normal output of the check node. Okay. So, these conditions, so let us give these numbers. So, this is 1, this is 2, and this is 3. So, equations one to 3 are known as the channel symmetry conditions. Sorry, as known as the variable and check node symmetry conditions. Now, what I would like to actually point out is that next is that when you are doing message passing decoding using the tanagraph. So, perhaps for this I will pull up again a picture from our last lecture. Okay, so here is the tanagraph. Okay. So, what is going to happen is that we are passing messages back and forth on this tanagraph, and let me just add one other small change. Let us also depict the input that is coming in from the channel to each of these nodes. Okay. So, this is the channel input. Now, what we want to actually, it turns out that well, so you are going to iteratively pass messages, and then when do you stop? Well, there is a certain number of, there are some conditions under which you can stop. For example, you can fix the number of iterations, after which you stop. But then once you stopped, all you have is a bunch of messages. How do you make decisions on the code symbols based on these messages? So it turns out that what you do is, since you are, regardless of whether you are operating over a binary symmetric channel or the AWGN channel, these messages are after all plus minus 1. So what you do is you stop, look at the sign of the message that you are sending out from a variable node. If that sign is positive, then you declare the corresponding variable signal to be positive. Okay, so you have multiple edges here, so you might want to take a majority of these, the signs of the messages along these edges, and so on. Okay, so that is how you will actually make a decision, by examining the sign of these messages. And then now there are many edges, and potentially each edge could be carrying a message whose sign is either in agreement with the correct sign of the corresponding code symbol or not. So we will actually regard an edge as being an error if its sign disagrees with the sign of the corresponding code symbol. Okay. So perhaps it is worth just making a quick note of that here. We will use the sign of the message going from, say, variable node to check node as an indication as to the value of V. So this, the value of this particular, of the corresponding code symbol, is what we are trying to decode. So we will indicate this as an estimate of, as our current estimate of the value of V. Of course, this estimate will keep changing, and so we will regard this message as being an error if the sign does not agree with the true value. Okay. So the message along an edge is said to be an error if its sign is not the true sign of the associated code symbol. Now, the messages are being passed in both directions. So, it is meaningful to talk about a message in either direction being an error, because for example, going from here to here, we look at the sign of this message and then compare it with the true value of this. If you are looking in for a message going from here to here, we compare the sign of this message with the true value of this particular code symbol. So, in both cases it is quite meaningful to talk about the value of, of a message being an error. So, once again, the sign of the message going from 8 to 6 is an indication of the value of 6. So, if that disagrees with the true value, true sign of 6, then we say that that message is an error. Now, what we want to actually show is that the number of incorrect messages passed is independent of the actual code word transmitted. we will now show proceed to show that the number of incorrect messages passed along the edges of the tanagraph during each iteration is independent of the transmitted code word. So, once we have shown that, to simplify the analysis, we will just assume that the transmitted code word was the all one code word, okay, because we will now show that the messages that are passed are independent of the actual code word. And what I will do is I will first let us go to this graph and I will try to explain the reasoning behind that. The reasoning behind this is this. Now, if the transmitted code word was the all one code word, then all these messages would initially take on the value at the output of the channel, which is certain y sub t. Now, if some of these code symbols were actually -1, then we know that there is an event, there is, I mean, the probability of y t being equal to, I mean, probability of the output taking on a certain value corresponding to 1 is equal to the probability that it takes on the value -1 corresponding to x t equal to -1. Okay. So, what that means, so let me just see. Yeah, so let me try to restate that. Let us go back actually to our symmetry assumptions. Okay. So, here if the incoming symbol changes sign, as it will, because if your code symbol changes sign, then your incoming message will also change sign, in which case what will happen is that the messages that are passed initially will actually change sign. And so, what is going to happen is that, yeah, so I think keeping in mind that I would like to actually get into Gallager's decoding algorithm, let me keep this brief. Basically, what happens is that your messages, the sign of the messages, whatever they are, if your transmitted code word was a 1, the number of agreements initially will be the same regardless of what the actual code word is, and that will propagate through the system, because let us say that initially when the messages go out, they are bearing their signs correspond to the signs of the incoming messages, and thereafter at a check bit what happens is that these signs get multiplied, and because of the nature of a parity check, it turns out that the sign of the message passed back from a check node to variable node is also multiplied by the corresponding value of the variable node. And so, this keeps continuing with the net effect that the sign of any message passed does not depend upon what the actual code word was, it remains the same, all right. So, let us do one thing, let us just put that down, and if time permits I might come back and explain that a little bit better. So, here okay. Let us now so we turn to examining a particular decoding algorithm that was introduced by Gallager. And in Gallager's decoding algorithm, what he actually was considering was the binary symmetric channel, where the input was either +1 or -1, and he specified certain specific variable and check node maps. He specified that at a variable node, the rule is that initially whatever the incoming message is, that message is actually passed out, and subsequently the message that is passed out of a variable node is precisely whatever comes in from the input of the channel, unless all the other messages override it. So, let us use this other figure here to explain that. So, initially here is your variable node and here is the output of the channel. Initially Gallager's algorithm says, look, my channel output is +or -1, I am just going to request the variable node to send out whatever it receives from the channel along all the outgoing edges. Thereafter, again we are still talking about a variable node. What it actually does is that it is going to send out, the messages are all +-1 in Gallager's decoding algorithm A. So, it is going to send out the channel input unless there is overriding evidence provided by all of the other inputs. If all of the other inputs have a sign that disagrees with the sign of the channel input, then it actually sends the reverse of the sign of the channel input. Otherwise, it continues to send whatever the channel input was. At a check node, what in Gallager's algorithm, messages again are all +-1, it just simply sends the product of the incoming messages. So, let us just put that down. So, size sub size sub 0 of m is simply equal to m. So, here I should mention that O is equal to +1 -1 and your message alphabet is also +1 -1. So, the initial map at a variable node is just this. Thereafter, size sub v of L of m 0 m1 m dv minus 1 is equal to okay, so is equal to minus m0 if mj equal to minus m0 for all and it is equal to M0 else. Okay, so what this actually means is that it is going to pay very close attention to what it receives from the channel, and it is going to transmit that symbol unless all of the other incoming messages have a sign that is different from the incoming message from the channel, in which case it will listen to these other messages and change the sign of the outgoing message. At a check node during any iteration, the message that is passed out is simply the product of all the incoming messages. All right. Now, so with this the decoding algorithm is very clear, right, because what we have done is we have identified the action during decoding that is actually taken by a variable node, and we have also identified the action taken by a check node during decoding. So, now we would like to actually do performance analysis. So, the question is, how well does this algorithm perform? Does this so we will handle this by doing something that is nowadays referred to as density evolution. So, we will do this, we will evaluate performance by carrying out density evolution by which we mean that we will determine or perhaps better estimate, we will estimate the number of incorrect messages passed during each iteration. And we will actually do this iteratively. Okay. So, to do that, it is so recall our assumption, we assume that the all one code word was transmitted. and we will introduce some symbols now. Let us say that P 1 of 0 denotes that the probability that the message passed by a variable node during the 0th iteration is equal to a plus 1, and P minus 1 0 is the same similarly for minus 1. So, here we are going to use the, now earlier in our we had used V and C to denote the variable and check nodes, but here what we are going to do is we are going to distinguish between variable and check nodes with regard to the probability distribution by actually using letters P to denote probabilities associated with variable node messages and Q for check node messages. And similarly, Q L 1 is the probability that on the Lth iteration the check node message is equal to 1, and similarly for minus 1. Okay, so, you would have Q minus 1 of L. Now, once we have that, it is possible to iteratively determine these expressions. Now, keeping in mind that our channel is a binary symmetric channel, and that the crossover probability is epsilon, we know that P 0 of 1 is equal to 1 minus epsilon, and that P minus 1 of 0 is equal to epsilon, because we assume that the all 0 code word was transmitted. There is another thing that I need to point out is, which is that when we are doing this analysis of the probability of messages being in error, see, if you assume that the transmitted code word was the all 1 code word, then if you look at your incoming messages, the probability that they are 1 is equal to 1 minus 1, the probability that they are equal to minus 1 is epsilon. Okay, one is 1 minus epsilon, the other is epsilon, and it is the same for all inputs, okay, because you are assuming that the all 1 code word was transmitted. So, the density function or the probability mass function of the initial message is the same for all inputs, and you can see thereafter by symmetry, because every node has on the left has the same degree, every node on the right has the same degree. By symmetry, what is going to happen is that the probability mass function associated with the message during an iteration does not depend upon the particular edge, it only depends upon the iteration and also the direction in which the messages are going. Are the messages going from variable to check node or vice versa? Okay. So, keeping this in mind, okay. So For this reason we do not have anything in this notation to denote a particular variable node, because for all variable nodes it is the same. Okay, so maybe it is worth making a note of that. Note that by symmetry the probability mass function of messages along an edge only depends upon the number of the iteration and we are using the symbol L to denote that. So, I E on L, as well as the direction of the message. That is the message going from a variable node to check node, or vice versa. All right. So, we have these initial probabilities. Thereafter, it is not hard to compute the other probabilities in succession. For example, if you look, let us say, at a variable node and we are interested in the PMF, the probability, let us say that the transmitted message along here is a 1. Now, this is a 1 if this is a 1 and not all of these are a -1, or if this is a -1 and all of those are 1. Okay. And now, here is where another interesting point comes up, and for that I will have to take you back to the computational tree. So, let me select this page, bring it into our current lecture. Okay. So, here is the computational tree, right, and let us get rid of these colors, we do not need them here anymore. We can just have the whole figure in one color. Now, we are doing this density evolution under the assumption that the transmitted code word is a 1. In particular, we know what the transmitted code word is. And now, let me just put down here. So, consider, let us say, a message that is passed during a certain iteration, let us say the second iteration, a message that is actually passed from a check node to a variable node. Now, the message that is going to be sent is a function of the incoming messages. Now, this incoming message in turn is a function of these incoming messages, and if you trace it back, eventually whatever the messages are dependent only on the inputs received across the channel. For example, the message here transmitted here during a certain iteration, this message is a function of, let us say you are talking about so the initially let us say there was a message that is passed here, and that on the second iteration there was a message that was passed from here to here. So, I can actually denote that by saying, let us say that this is on L equal to 2, and this was the case when L is equal to 1, and this was the message passed on L equal to 0. Remember that a particular iteration consists of a message from a check node to variable node and then back. Okay. So, this was one iteration, this was the initial phase. So, during the second iteration, a message that is passed here is a function of what was incoming here, right. But what was incoming here is a function of what was incoming here, and so on. If you trace it back, this message is a function only of these received symbols y1 through y8. Okay. So, this message, so we will make a note of that. This message is only a function of y1 through y8. Now, in similar vein, if you ask yourself the question, what is this message a function of? Okay. And then you see that this message is a function of y9 through y16. Now, given the transmitted symbol, the received symbols are only a function of the channel noise, and therefore they are independent. And therefore, these messages which are a function of these independent random variables are also independent. Okay. So, when we are actually computing probabilities and we want to find out the probability of an outgoing message given probabilities of the incoming message, we are free to make use of this independence. Okay. So, thus, so in conclusion here, let me just write these messages are independent. I am going to try to use a fine point here. These messages are independent. Okay. So, making use of this, it follows that, so we have already started out, and let me copy from what we had earlier, which was these probabilities. Thereafter, we can actually say that a P minus 1 of L is P minus 1 of 0 times 1 minus 1 minus q minus 1 of L to the dV minus 1 plus P1 of 0 times q minus 1 of L to the dV minus 1. So, what does this expression tell us? It is actually quite straightforward. It is just saying that, look, if you are looking for the probability that a variable node is going to pass a minus 1 on the Lth iteration, well, that can happen only if the channel input is a 1 and not all the inputs that it receives from the check node are all 1, right. So, this is probability of them being minus 1, this is the probability that they are 1, and since these messages are independent, I can raise it to the power when I want to compute the joint probability of them being all equal to 1. So, provided they are all not equal to 1. Okay, so, we will just make a note of that, that this quantity here really represents the probability that not all incoming messages are equal to plus 1. And a side remark is that this uses the independence which I remarked upon a few minutes ago. Okay. So, now the Q's represent the probabilities of messages going from a check node to variable node. Okay. So, now we have the P minus 1s in terms of the Q's. So, how about the Q's themselves? So, the Q's can also be computed in this way. We can actually say, so let us go back here and look at the picture of a check node. So, the probability that we are trying to evaluate now is saying, look, here is a check node and I am going to pass a message from a check node to variable node, and I want to know what is the probability that it is minus 1 or plus 1. Keep in mind that an iteration begins by a message from a check node to a variable node. So, if we are talking about the Lth iteration here, the incoming messages are messages that were transmitted during the L minus 1th iteration. So, that is just to get our notation straight. Now, how do you compute that? So, that is a little bit more trickier. The way we will compute it, and this is the way that Gallager computed it, is to say that Q u d c of L is the sum u1 the sum over u1 u2 u dc minus 1 subject to sigma uj equal to udc, and the product j equal to 1 to dc minus 1 p uj of L minus 1. Okay. So, what this is actually saying is, look, after all, the probability that udc is a 1 perhaps the picture, perhaps so we just have about 2 minutes left. Let me just draw a picture here. So, the picture is one in which you have a check node here, and you are asking the question, what is the probability that this outgoing message is a 1, and here are the incoming messages. So, this is going to node UDC, this is coming from U1, this is coming from UDC minus 1. Okay. So, there are some other incoming nodes as well. So, what this computation here is saying is that, look, the probability that this message is going to be a 1 is if is all combinations of the incoming messages which are such. Now, I have written some over here which needs some explanation. So, let me just do this, let me just add mod 2, remind you that x I is minus 1 to the u I, and we will continue this particular calculation in the next lecture. Let us just end with a quick summary. So, we looked at the goal was to look at Gallager decoding algorithm, and I first introduced the message passing terminology in terms of describing the input and output alphabets as well as the maps. Then we specified the decoding algorithm, and we were doing what is called density evolution on this graph. We will continue next time.